Welcome to third lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is fundamentals of friction and wear. It's very common topic, but question comes, can we really cover in one lecture itself this kind of fundamentals? We'll try. We'll try to summarize in a much more fruitful way. But before that, we want to just summarize what we have covered in last two lectures. It was mentioned that tribology is a surface phenomena, and surface roughness plays a significant role in defining friction and wear. Not only this, even trapping the wear debris and acting as a lubricant reservoir. So these are the very important aspects, and this kind of ideal surface was shown. It has some sort of load bearing areas, and it has a valleys to trap particles, to trap lubricant, or we say to keep as a lubricant for reserve. And this can also be completed, we can achieve by super finishing operation. If we are not able to do the super finishing operation because of the manufacturing, then good rigorous running in process is really required, meticulous running in process is really required. What additional thing was mentioned, that friction and wear are not intrinsic material properties. It cannot be defined that these are the material properties, but these properties are belonging to the system. They are system properties in which materials are playing a role, so they operate as one of the variable. Not only this, the controlling wear and friction are crucial for almost all machineries which having a tribo surfaces, from energy efficiency point of view, from durability point of view, and reliability point of view. Also, it was mentioned the 1/5 of the world's energy is spent on combating the friction, to counter the friction, to overcome the friction, and particularly in transportation, where the friction is consuming almost 1/3 of the energy. Also, it was mentioned that friction and wear losses affect efficiency. They have an impact on efficiency, and then we really require to explore different methods to really minimize this. There's also that what we have already covered, maybe say learned about the surface friction. There are some common knowledge available. Generally say the friction force is proportional to load. We need to figure out whether really it happens or not. Another thing, it is often says the coefficient of friction is, in a static case, it will be always higher than kinetic coefficient of friction. It may be, may not be. However, this need to be investigated scientifically. That's important aspect. We most of the cover the theories are related to dry friction, but we want to cover also the mixed lubrication, sometimes we call it starred lubrication, and completely lubricated states. So friction in dry case will be different, friction in mixed lubrication will be different, and friction in well lubricated state will be different. We can really play an important role by reducing energy losses. How? We can investigate a newer material, we can think about new material, so we will be providing some sort of pointers. We can really design lubricants, we can make a necessary adjustment on the surfaces also. So these are important aspects which are really required to explore in detail. We also in lecture 2 we have shown this kind of curve, what we call a modified Sommerfeld number, and then not only friction, coefficient of friction, but it was a normalized wear as well as a surface roughness related parameter. Specific film thickness was also shown, and it was shown very clearly that whenever there is a hydrodynamic region, then only the mix friction and wear will differ, otherwise they follow some sort of a trend. They go almost a similar kind of trend. However, this may be in few particular cases, but in a hydrodynamics domain, wear becomes almost zero, and friction increases. So we need to really understand and think about alternative solution to minimize energy consumption. Present lecture we are trying to focus mostly on the dry lubrication, and to really think about friction and wear in a proper way, we need to think about a micro scale. Reason being, asperities are there and the asperities are going to affect friction and wear. So it is important. And this was also covered the running and behavior of tribological components or tribopairs. We say after running in, quite possible that surface will leave some asperities, or we say the shaving of asperities will happen, and it can fill the other surface gaps also. So it can really smoothen the surface, reduce the surface roughness, and then increase so they improve the performance, the friction performance and wear performance. This was discussed. Now, what does it really need? What we understood and what does it really need? We say consolidate friction and wear mechanism in cohesive model, because we are still treating friction and wear in separate manner. Can we think about cohesive manner? And that's what has been shown here in dry case and boundary lubrication, mixed lubrication. They can be treated in a cohesive manner. However, we really require a good models to understand, to predict, to comprehend the energy losses, to really investigate the heat generation and overall economic losses. So this is what a need. We really require this kind of model to uh, go ahead with the comprehension of energy loss, heat generation and economic losses. Another one was a linking of friction wear to phenomena like roughness changes, which happens in dynamic situation. It's not an initial surface roughness in dynamic situation. Reason being, I've seen the many times a smoother surface, they become a rough after few hours of operation. So unless we are able to estimate, unless we are able to predict, we will not be able to do get some sort of remedial solution. We cannot just think, but we need to really do modeling and predict properly, and then establish right relations. So this is very important. The wear particle formation, how the wear particles are formed, and whether they will be harmful, can it be, we can be converted into the usefulness of those part, how do we make a useful those particles is important. Another one is the microstructure changes, which can be really modeled. So these are the some needs which are really requiring this kind of course and investigation, particularly in tribology. Now, when you think about the tribological behavior at a microscopic level, this curve comes first in our mind. We said earlier the coefficient of friction value will change with the time. Initially, coefficient of friction may be on higher side, then it will reach to the established condition, and based on the further condition or surface degradation or environmental degradation, it can really again rise back into this form. That means there is stability of friction and it can rise back. And same thing what we say for the wear, this is exactly the behavior of the wear which is predicted. We say failure rate, and initially the beginning or running in period we say infant mortality, where the failure rate is decreasing with a time. After that reaches to the steady state, so this is a steady state, and towards a law end where the surface degradation is substantial, we say there is an end of life of the component, because the failure rate is going to increase. So there is some sort of correlation between friction and wear. They follow almost similar kind of trend. However, there will be exceptional things, I'm not denying it, but these are, there is a correlation. Now we think about the wear, we say there are two primarily mechanisms. This doesn't mean that these are only mechanism, because I know the literature say there are 34 kind of the wear mechanism. We don't want to go into that detail, but majority is adhesive and abrasive, and these two wear together they contribute almost 75% of the wear rate or wear mechanisms. We say that what is a adhesive wear? Adhesive wear occurs when the interaction between two opposing asperities is characterized by intramolecular attraction. When the two surfaces they come into contact, there's a one asperity, there's another asperity, and the molecule of this asperity and molecule of this asperity, they try to intermingle, or maybe say make some sort of bond, intermolecular bond, and then this becomes a weld. The major issue comes, this is a I say tau S1, this is a tau S2, and this is a tau interface. The major issue comes when the tau interface is a greater than tau S1, or maybe say tau interface is greater than tau S2. Reason, this is a shear strength of surface 1, shear strength of surface 2, this is a shear strength of surface interface. So this is a major issue. And then in previous lecture we say that if interface is made proper, then things will be much easier. That's why we say tribo interface with complete calculation. Now in the present lecture, we will try to really make some sort of relation, may not be 100% correct, but it gives us some sort of indication. How do we make a tau I is almost lesser than, or is almost negligible compared to tau Si, or tau I lesser than tau Si2. This way we will do investigation on that. So this is the intermolecular another force with the adhesion, another force which comes because of the abrasion. We say there are asperities which will try to display the material. If there is asperity something like this, and there is a opponent surface is something like this, so this asperities as it moves in a direction, they try to remove the material from this surface, and the material will get removed, and naturally the wear will increase, and this is what we call abrasive wear. We will detail abrasive wear in lecture 4 in much more depth. However, we are trying to introduce this topic because it is going to really develop some sort of fundamental concepts and some sort of model which will provide some understanding to us. So you see, it causes one surface to display by another one. That's what I shown, that this is one material is another material, and material get displayed because of the harder material or because of the hard asperities. So system efficiently counteracts sliding. That means that's why the friction force comes into this. Now in this case also, that when we are trying to the slide, and this is a one surface, another surface interface. When we are trying to push, naturally there is a friction force, and friction force will try to rupture the tau I, and if it is not able to rupture tau I, and suppose tau Si2 is a laser, then this fragment will be removed. So this is an important aspect. So in the both the cases, the friction is also coming and wear is coming. Mechanism are same for both adhesive mechanism, abrasive mechanism. We are trying to say the mechanisms are same. That's why we say there is a time we are trying to go ahead with a cohesive model. And we say that particularly this abrasion or abrasive wear is a major mechanism for the sliding, dry sliding. Reason being, the particularly dry rough surface. If the roughness is not there, then this will not be an issue. But if there is a rough surface, then abrasive wear will be dominating compared to the adhesive wear. If the surface is smoother, then adhesive wear will dominate. Of course, we are talking here only two body abrasion. We are not talking a three body abrasion, which will be discussed. These various mechanism will be discussed in detail in lecture 4, next lecture of this course. Now let's take two examples. One is adhesive wear, left hand side we are showing, and right hand side we are showing abrasive wear. We are trying to summarize, consolidate in a smaller, well, lesser number of slides. You can see here the asperities which are coming into contact. Green color is maybe say S1, this is S2, then there is a interface happening over here. The two asperities, they are coming into contact. There may be elastic deformation, maybe plastic deformation, maybe rupture also. So when asperities is moving on other asperities, then slowly it is there is you are able to see there is some sort of interaction. Now completely overlapped, then again is departing to other side, and finally it is departed. So we are saying one aspirative model, how it is approaching to the second surface, how it is overlapping, completely covering, and third, fourth, it is really departing. This is what comes in adhesive wear. Similar kind of abrasive wear, we are assuming there is a hard particle, kind of this kind of a conical asperities, and then trying to and blow the softer material. So we will try to develop a relation for these two cases. We say when we talk about the adhesive wear, and we are applying a normal load, in this case W. The normal load, when particularly where here the completely covered, how it will be given, because this is a diameter is 2a, and we can take area pi a square, and we know this is plastic deformation happens, or rupture or removal of the surface happen when we multiply with the hardness. So hardness of the soft material, so H is a hardness of the soft material in this case. So this is what happened, and then we are assuming some sort of multiplication constant. We do not know whether 100% asperities will be removed, only 1% will be removed, 2% will be removed. We do not know. So we are just using the one constant k, some fraction will be removed. That's what we are assuming. Now this can be applied to n asperities, assuming each asperity has a some radius that has been given here I1 to n, and we do not know how many asperities, where assumption is a m number of asperities, and area, maybe radius of each asperity is ai. It can be same, it can be different also. We are not worried that much about this. However, the hardness is same across the complete surface. It's not that one patch has a high hardness, other patch has a low hardness, and it's not. So this overall load, which is a normal load, has come on the surface, is at the constant, multiplication constant. It can be lesser than 1, more or less it is always a lesser than 1. It can be 0.1, 0.01, 0.001, 0.00001, depends how what is the probability of the failure of the junction. So this is what can be given in terms of the load. We are expressing in terms of hardness and the radius is unknown and number of asperities are unknown. Now how much wear on the wear has been, wear of the volume will occur. So that says that here the 2 is a sliding distance. When asperities is coming, we know that only asperities are coming into contact. Complete surface is not coming into contact. So we are assuming the sliding distance, and where volume has been given here, and we are assuming hemispherical asperity, and assumption that whole asperities will be removed. We know that hemispherical asperities volume will be given by 2 by 3 pi a cube. We substitute divide by 2 way, we will get something like this, pi a square by 3. That means on where volume per unit sliding distance is being given by this relation. Now if we integrate for the all asperities from I1 to n, number of particle n, so n is a number of asperities. Right, so this can be given. Now one good point is that we do not know n, we do not know ai, but in the both expression, in here v and here the w expression, pi a I square is coming, and the same summation I1 to n. So this is the beauty, we can substitute from one to other, and we can say where volume is can be given by this relation, and the w is here, w by h, and then is w by h, and is also there 1 by k, and here the 3 is also coming. So this is a wear volume per unit sliding distance, particularly we say when all asperities, and we can include a sliding distance as equal to L, overall sliding distance, that can be multiplied with this, so that we say wear volume. Here it was a wear volume per unit sliding distance, wear volume can be given in this relation, and this is known as the Archard equation. This is the author who has derived this relation. I'm trying to simplify and show in a manner. Now as there is already we are this constant k1 and 3, we know the constant k1 is constant and 3 is also the number, so I can replace this with another constant k2. That means wear volume can be given in terms of normal load which is applied, overall sliding distance, hardness of the softer material, and multiplication with some constant. Now coming to the second relation, that's abrasive relation, that's Rabinowicz has given this relation. What has been mentioned here, that normal load which has been applied, and again here we are assuming that the conical the asperity, and then it also has particularly when it is coming in a contact, assuming all asperities are coming at the same height, same kind of treatment. So that area, and then this 2a has been given as a length, and overall if I project it, this comes in the pi a square as a area, half of that. And that's what we say, that normal load has been given in terms of this relation. So normal load can be rearranged, because a we do not know exactly, and we will bring a where volume equation. Here the it will be the projected area, this is the projected area into sliding distance. X, particularly this can be given in terms of a and alpha. Alpha is a half of the cone angle that has been given over here. So substituting it, and then we rearrange this complete thing, because where volume can be given in terms of a normal load, in terms of sliding distance, in terms of hardness also. So if we rearrange this equation, where volume overall is can be given the 2 by pi tan alpha. This is the normal load, normal sliding distance, and hardness, and this can be treated as a one constant. However, this constant will vary depending on the condition of operation, but more or less this relation, this particularly relation what we are showing, and this relation more or less are the same. There is a wear volume, there is a normal load, there is a sliding distance, there is a hardness, and there is a multiplication constant also. So this is what has been given. Now this what we have already shown about top curve. There we say that this is the what we when we are really giving this kind of model, that model is going to represent only b to c portion. It is not going to give a representation of AB or CD. That means a fatal wear rate it will not give, in initial wear rate it will not come, right. So the predictive model, whatever the Archard or Rabinowicz we use, this is for the steady state wear rate BC. There's a B to C zone only we are trying to predict. A to B and C to D we are not predicting, right. So this is what important aspect to consider. Now coming to the constant k, now this constant k or k1 whatever we say depends on the what is really required. In this case particularly, if it is a k is equal to 1, what is the meaning of that? Every junction involved in the process produces a wear fragment, and that's a one point. Now if k is equal to zero point 0.1, we say only 1/10 of the friction junction produces a wear fragment. So this is important, the 1/10 of this. Now most of the time we have observed that the k comes out to be around 10 raised to minus 7. That means only 1 in a 10 million produces the wear fragment, and this is a typical fatigue wear kind of process, where the fatigue of the asperitic or maybe the fatigue of the junction comes into picture, and the constant is much lower. However, in case of the dry case, wear coefficient will be in higher side, and lubricated case wear coefficient will be much lower side. We do not know thing, but many times people use this kind of relation. They do experiment, and then finally whatever the constant k comes, they try to use for the simulation purpose. So this is an important aspect to consider. Let's to understand this, maybe we can consider one example for this exercise. I mean this kind of exercise, what the example say, there is a hard steel surface consisting of an array of conical asperities. These are all hypothetical. Average cone angle has been given as a 120 degree. So what we are saying in this case particularly, this angle the 2 alpha is given as a and the 2 alpha has been given as a 120 degree in this case. So that has been given, and then we want the wear coefficient to be estimated for this case. And then second thing is that if the cone angle changes from 50 degree to 180 degree, how the wear coefficient is going to change. So it is just a kind of exercise which we are trying to understand. In reality, quite possible initially cone angle was a 50 degree, and after running in it has reached to the 160 degree, 170 degree, or it becomes a completely flat 180 degree. There is a possibility. However, when we do designing, we try to really play with the numbers too, so that we our understanding improves in this case. So if I try to solve this problem, we say angle conical asperacy angle has been given 120 degree, half angle, which is what we really required, is a and the 60 degree, applied load is a 15 Newton, and wear coefficient, which Archard equation has from the from not Archard equation, from Rabinowicz equation, we say it has been generally given in terms of 2 by pi 10 alpha. So this is a constant k. Now if I do write a MATLAB code, we are what we are saying that the represent theta from 50 to 180 degree by increment 1, so that we can really plot and we can get the results. Alpha will be half of the theta, so instead of 2 alpha here, we are writing theta to distinguish it, and then alpha we are writing again as a theta by 2. Load has been given in this case. This is a simple MATLAB code. Now we are giving expression k in terms of pi is being given here, and then and 10 alpha already being given, and we are giving in the degree, so that's why we are writing directly the degree to radian. That means if we don't write, we have a alpha angle available in radian, we directly will substitute to calculate the results. After that, we are trying to plot k, the severe coefficient with the theta, and that has plot has come something like this. We can see here asperity angle in theta degree. So it start from 150 to 180 degree, and then where coefficient initially is on a higher side, it should be much lesser. That means we don't believe up to the level, that means that this is lesser than 70 degree. On the 70 degree cone angle is pretty difficult. When we are saying that okay has to be lesser than 1, that means this portion will not be reality as such. Now coming to the 70 degree to 180 degree, you can see the coefficient is continuously changing and almost reaching to the negligible level. That means when a flat surface is a flat, this cone angle will not be there, abrasive wear will not occur. So this is what is just to get understanding then how do we go for the betterment of the surfaces, how to design better surface to get a good results overall. That what we say here, this is a perfect surface we want it, and in this case, and then we said in the lecture the coefficient of friction, sorry, wear coefficient which is being required particularly for 120 degree has been calculated as a 0.368 or maybe say 0.37 in this situation. And then one important aspect comes, and if you read the book of the Professor Ludemas, he says that more than 2000 wear equations are existing, but there's no general equation available, so we need to interpret. Exact value is not being given. That's why the data driven approach comes into picture. When the no perfect equation is available, and then every equation will change as per the situation, so why not we go with data driven approach. That's why this course has been initiated and started for that purpose. You say for comparison purpose, dimensionless wear coefficient, which has been calculated in this case, can be utilized. So we can do a relative performance, not absolute but relative performance. What will be the wear rate between two material, two different situations, and then what we say, and if wear rate, or but particularly k, the value of the k is more than 0.0 10 raised to minus 3 or 0.001, then it is going for unacceptable case. On a more practical case, durability side, the wear coefficient should be lesser than 0.7. If you are able to go ahead with the solid lubricant or materials which we select, which can provide a wear coefficient lesser than minus 10 raised to minus 7, then those are acceptable. And if it is a wear coefficient is going on a higher side, then we require some changes to be done so that wear coefficient can come down, can be reduced. However, it is again very difficult to think about whether it is adhesive wear, abrasive wear, because both the things will happen simultaneously. Some places there will be adhesive wear, some places in will be the abrasive wear. So if we are using one common equation and there is a common way to find out the coefficient, that will always help us. That means one constant. Now if we don't know whether it is happening because of abrasion, because of adhesion, but where coefficient is a lesser than 10 raised to minus 7, then is acceptable design. Otherwise we need to really do remedial action for that purpose. Now, in the same the way we have covered wear, now we can think about friction. Again, same thing. Adhesion. We say that the two surfaces when come into contact, there is a cold junction and it need to be ruptured. So that's adhesion. Now, if a conical asperities is a harder, and then it will not break, and we need to plow the soft surface. That comes abrasion kind of thing in this case. So, however, we are trying to instead of abrasion, we say deformation, because it is going to deform the surface. And adhesion is the same mechanism what we have followed for the abrasive adhesive wear in the case. Now finally it should be the summation, and friction force will be, because as I say, the both will be simultaneously, some portion because of adhesion, some portion because of deformation. It should be summed up. And there are some extreme situation, we say in case of the lubricated or well lubricated, they will not, two surfaces will not come into contact at all, so adhesion force will be almost zero. Of course, if the two surfaces do not come into contact, then quite possible the even the abrasion will not occur. However, even if it is a boundary lubrication, a mixed lubrication, two surfaces are coming into contact, but they are gliding. They are not really creating the friction, resisting the motion. Then again, this constant, or maybe say addition friction will be lesser. Coming to the smoother surface, we say that for light load condition, smoother surface, there will not be deformation. Naturally, this where our friction will be much lesser. So, in short, we can summarize that there are two main mechanisms of the friction: deformation and adhesion. And adhesion will play almost negligible role in a lubricated case. If the surfaces are perfectly smooth, then deformation also will not be there. And however, when the smooth surfaces are smoother, then intermolecular attraction will be on much higher side, then quite possible adhesion will come into the picture. While in case of the lubricated case, even we know the adhesion will be almost negligible, even the deformation also will be lesser. So that's why we always prefer lubricated case whenever there is a need. And we are fortunate that our surfaces have, maybe say, metallic surfaces or fiber surfaces, they have a coating on that, that's environmental, maybe oxide layer coating, that really prevent its damage. So that's always useful, and we should utilize that kind of formation of oxide. And if the oxides are getting ruptured, we should bring the situation where the oxygen can really act chemical, or maybe say chlorine can act, sulfur can act, phosphorus can act, whichever the active material with the surfaces which are really useful to reduce the wear. However, we need to also keep in our mind that those additives need to be environmental friendly. We know the sulfur and phosphorus and how they have been restricted, and we can't use freely. So those disadvantages are also there. So we require a perfect solution, almost zero energy consumption, zero wear rate, but it should also, there should be environmental friendly additives, while there will be some sort of restriction or legal restriction on that. Now, some sort of a theory development, we can say that this conical like asperities, which is trying to plow the surface, we can give relation in terms, particularly area overall will be if the number of asperities are n, and each has a cone has a radius r, can be given in this form. Of course, we say r we do not know. Assuming all asperities will be of the same dimension is a very hypothetical, no realistic, but this assumption, and then we will try to play so that at least we get some sort of feeling about a abrasive friction or friction due to deformation. Now, if we calculate the normal load we know that area into hardness, that is what has been given. Similarly, friction force can be projected area is something like RH of the each asperity into number of asperity into hardness. If I calculate a coefficient of friction, that's a ratio F divided by W, it comes out to be something like a 2 pi cot theta, or say 2 divide by pi tan theta, which was calculated same thing which was calculated for the wear, particularly constant, not a friction but a constant. So here this constant can be substituted in that equation, there's a possibility. However, where there's no logic as such, we are trying to, here we say that this is a gross approximation, we are trying to interpret the results in a form. Now if I calculate the theta, and mu. As a theta is increasing, in this case you can see that the coefficient of friction is changing. Now if theta is this theta is a half angle, it's not a the 2 alpha, and there we use alpha, that there we use alpha, here we are using theta. Now when the this theta or alpha are 80 degree, coefficient of friction is much less. However, if there is a theta is more like in a 30 degree, naturally coefficient of friction is on higher side. So again, from their point of view, as you say, the k has to be lesser than 1. We rejected half angle as a lesser than 60 degree. Same thing in this case. So this can give justification that because of asperities, what will be the coefficient of friction. However, again, as I say, this is the hypothetical example. We are trying to understand that how the results will change during running condition. So another coefficient of friction is because of the adhesion, and adhesion is very common example. When we write with a chalk on a board, it is adhesion that the layer is getting transferred. Here we are showing a kind of seal, a carbon graphite seal. When we rub against steel shaft, one layer is getting transferred. So adhesive wear is that way that softer surface will get transferred, will transfer one layer on a opponent or opposite surface. Same thing was realized earlier when the beginning itself. We say that if you steel or the brass pin is dipped into the indium and then retracted back like something like this, we will find some layer is getting transferred over here. So indium layer transfer the layer on opponent component, opponent surface. So this is what adhesive wear. Now what I said very clearly, in this case particularly, this is a tau s1 and the interface tau I, and here this tau s2. Now what I can say here in this situation, particularly tau I is greater than tau s2, that's why layer is getting transferred. Same thing when we write with a chalk on a board, interfacial strength between the chalk and the board, tau I will be higher compared to the strength, shear strength of the chalk itself. That's why that is happening. So this is what we go ahead, and now if we try to write in mathematical form, we say area of contact can be given by applied normal load divided by hardness, because the layer is getting transferred, and that's why the hardness comes into picture. However, if we are trying to move surface relative surface, area can be calculated from this, and then we need to overcome the shear strength to to really move the surfaces. That's why as, and then when we write a relation something like that, the mu a will be turned out to be a s divided by h, that means shear strength divided by hardness. However, it doesn't convey much meaning. Reason being, the shear strength is the material property, hardness is the material property, hardness is the material surface, not the surface property kind of thing. Hardness not exactly material property, then it should not vary significantly. But we have seen in slightly different situation mu a changes drastically. That means something is missing in this relation, and we need to really think slightly different than what we are really projecting. So that's why the theory came like a junction growth theory. Again, this is a kind of not 100% correct, but it gives us some sort of a feeling about the friction. Some people say there is a modified Bowden and Tabor theory. What is the meaning here? We are saying that the normal load is applied and friction force, the tangential force, we are trying to separate, and there is an area of contact here. And then when we try to use some sort of equations, particularly principal stress theory or we say Mohr theory, then we can really drive the relation in terms of stresses. And what are those stresses? Something like this: sigma 1 is the principal stress, and basically this is a situation, and we try to find out sigma 1 sigma 2 in time in the direction of sigma 1 and sigma 2, shear strength will be 0. That's why we are trying to utilize in this manner. Sigma x and sigma y has been shown over here, and then this is a simple relation which we can utilize to solve the friction equation. However, as I say, that may not be 100% all assumption correct, but it gives a feeling that what is the overall behavior of friction. And here we are saying the sigma x is equal 0, we are applying a load or normal load only, so sigma y can be given something like delta w divided by delta a or area, and tau x can be given as a shear strength kind of thing, and is a delta f divided by delta a. So these are the relations can be given. As I said, principal stress theory or more theory can be utilized for this case, and we have expressed the relation. Now we subtract equation. This is equation 1, this is equation 2. We subtract 2 from 1. What we got a sigma 1 minus sigma 2 into the del area into this relation. And we know that this difference in stresses can be equal to the yield strength as such. So in terms of yield strength, and we express normal load, friction force and area, and we know very well that applied load will be constant and yield strength of the material will remain constant. It may change to little bit but not major way. And we also know the tau max can be given as a sigma 1 minus sigma 2 divided by 2, or 50% of the yield strength as such. Now what is really coming out very interesting from this relation and why we are doing here is something like this is a constant, this is a constant. That means whenever there is a friction force is going to increase area of contact. That means whatever initial contact, it will enhance, it will increase by percentage. It can be 50%, it can be 100% also, and that's what we say that here the friction force is related to the area, and that's a very major finding, a big finding as such. As area of contact increases, friction force is going to increase. This is however people have authors or maybe researchers have also contract, right? But it gives a good feeling or good understanding about friction force, so why not we shall use this one. So this is what has been given. Now we also know that when we apply force on a surface, like this take example have we taken here, that's like a applied load is 100 newton and coefficient of friction is a 0.5, what we are calculating. If you apply only 20 newton force in a direction, we know the surface will not move. If 40 newton, surface will not move. Only 15 newton, which is that's 0.5 into 100, 15 newton, only surface will move that. That means this is a portion we can say initially there was area of contact and continuously increasing, and here that junction growth is broken, maybe say junction is a broken as such, and that has exactly been mentioned over here. We are assuming area increases to maximum, a maximum, and then junction breaks. Now here we are saying that the interfacial strength is tau I. The tau I into A max will give me the friction force. Right. So this is where we say the tribological interface, the lecture 2 which we study is important and then plays important role to understand overall friction force and wear rate also. So coefficient of friction F max divided by normal load. We already have given a friction force in terms of tau I and A max, and W we can calculate from here. This is a sigma y square minus tau, we can say tau A square, and this A already has reached to the A max, that can be given this relation, and we can remove A max and A max because we don't really require rearrange. The coefficient of friction can be given in this relation term. The 0.5 divided by this tau y is a strength of the material, the softer material. Tau I is a interfacial strength, and then minus 1. Now here we are assuming tau I will be having a lesser strength compared to tau y. This is not otherwise this whole term will be negative, and that means the tau y divided tau I has to be greater than 1. If it is not, then this theory will not be applicable and we need to reject this theory. So however, for this purpose, if we calculate, what we find tau I by the interfacial strength, if it is 1% of the tau I, coefficient of friction will be very low. If it reaching to 80%, then coefficient of friction is 0.667. So this is looks to be somewhat realistic, and predictable. Yeah, this is a good results, giving some results to us. So what we say, generally interface of the material, tribo interface will be around 5 to 20% weaker than the bulk material. What is the meaning of that? That tau y by tau y, if you don't treat, we don't do a heat treatment and maybe surface treatment, increase the hardness, quite possible that interface may be 80% of the than the bulk material itself. So coefficient of friction turns out to be around 0.6 to 0.7. That is also acceptable, or maybe already we have seen in number of material pair coefficient of friction comes in that manner. However, another thing, interesting thing comes a concept of lubrication. If I provide a lubricant at the interface, we know the lubricant will not have a shear strength, and immediately the coefficient of friction will turn out to be much lesser. So this gives indication that the lubrication plays very important, whether you want to play minimize the wear, whether you want to minimize the friction, becomes very important. Now how the lubrication happens, that depends. It can be atmospheric layer, it can be contamination, it can be anything. Nothing lubrication means a liquid lubrication or something like that. It can be anything which provides a gliding surface. It can be ice, it can be water, anything. So that way the concept of lubrication plays important role, and we need to consider. Now just to exemplify what I explained, I had again taken one example. What we see that here particularly is the force of friction is required to shear tribo interface. That's what I mentioned. Now here we can go ahead with lubricant film, we can go with a boundary lubricant, or we can go the boundary between the two surfaces. To exemplify this, what we have seen, the determine coefficient of friction between smooth surfaces made of aluminum and steel, under dry case, under oily case, and a solid lubricated case. So in out of three, only dry case is kept dry. In this oily case, it can be have additives, or can be a solid lubricated cases. We have other things. Solid lubricant be utilized. Now here we are seeing the shear strength of the steel is a 300 megapascal, and shear strength of the aluminum is 100 megapascal. And we know the tau I what we selected will be of the softer material. That's what where we say the lower material strength. That means we will consider only 100 megapascal. And what we need to calculate, interface shear strength to mega. And in one case, particularly when there's a solid dry case, solid to solid surface, then interface shear strength is 2 megapascal. When it's oily case, the 50 kilopascal, and when it comes to the solid lubricant, it shear strength is around 150 kilopascal. So we need to find out the coefficient of friction, and coefficient of friction equation is something like this only. Here we are taking the tau y for aluminum, that's what I mentioned. We are not taking for steel, reason being we need to compare with a softer material. That is more important. Don't commit mistake by taking a harder material. And this tau I as late is being given in one case 2 megapascal, other case 50 kilopascal, and third case what 50 kilopascal. So I can write a simple one MATLAB code to for this purpose. That's why I've written here. Tau y is 100 kilopascal in this case, sorry 100 megapascal in this case, but 100 into 10 is to 3 kilopascal. And tau, because this is a ratio, we need to express in the same terms. So I have expressed everything in kPa. So tau y is 100 into 10 is to 3. Tau I oily is a 50. Tau I solid lubricant is a 150. Tau I 100 dry is a 2000. That's what 2 into 1000 is a 2000. All are in a KPI, KPA, 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 and KPA here. Now coefficient of friction has been given in the case of dry. We are relating tau y will be same in all three cases, while tau I will be changed in dry case, oily case, solid lubricant case. And finally what we are getting result, coefficient of friction under dry case is a 0.01, coefficient of friction and the oil case is 0.00025, and solid case is a 0.00075. So this is the cases has been given. Of course this is maybe must be 0.3 or something like that. So this is example to exemplify this relation and the question of friction. Now question comes, how do we avoid a junction growth? We know very well if there is a contamination, then it will reduce the junction growth. That's why we have written here few molecular thick oxide layer on the surface is necessary to minimize the interface shear strength to produce a lower shear strength. And we need to make sure that oxide layer should be there, and in case if it is getting rupture, then there should be a refurbishment of the layer. That means there should be sufficient environment to make the layer again. It should not happen the one layer, once the layer has been removed and there's no refurbishment of the lubricant layer, and then there will be problem. Another thing is that what we say, the roughness has to be lesser than zero point 0.2 micron. That's important, and particularly we are talking about RQ, the 0.2 micron, you try to keep it lower than zero point 0.2 micron, because that is really going to help us. Otherwise it will cause a damage of the protective layer or contamination layer. We need to minimize that. If possible, go with a thin film lubrication. As I mentioned earlier, that we are now moving from thick lubrication to thin film lubrication. If you are able to maintain the thin lubricant, that will be very good. Finally comes ductility. Particularly to minimize the junction growth, we say reduce ductility, go for lesser ductility, so the junction really rockets rupture. So from that point of view, slightly brittle material or ceramic material will be better option compared to the metal surface. So this is these are the some suggestion to minimize coefficient of friction and particularly junction growth from that point. Now one more point comes, what we have derived equation particularly for the dry cases. Now what will happen in the lubricated cases? We really give wear volume in terms of, again, wear coefficient in terms of W, L and H. So number of researcher, they have done work on that. They say it can be, the wear volume can be given in terms of W, L and H, and we here we write down KB. Now, whether really can be given, we will use a machine learning algorithm to figure out what is the weightage of W, what is the weightage of length, what is the weightage of H, what is the weightage of coefficient. When we have many parameters, we can really prioritize which factor is playing more role, like whether W is playing more role, hardness is playing more role, length is playing more role. However, for whatever the available literature, we need to first go through that literature so that we can extract the feature. Again, here the features are W, L and H and the material thing. So here we are saying here particularly for this partial lubrication, which we call the boundary lubrication case, KB has been kept here, and there are already literature data which says that hydrodynamic coefficient in case of the hydrodynamic lubrication, wear coefficient will be lesser than 10 to minus 30. In elastohydromal lubrication, coefficient of friction, coefficient of wear will be lesser than 10 to minus 9. Boundary lubrication, it will be lesser than 10 to minus 6. Again, solid lubrication, it comes around with 10 to minus 6. Of course, they have given a fixed value, it is not varying. In case of the dry case, it gives a value 10 to minus 2 to 10 to minus 6. And here, if I take this as a table, and I can say, yeah, we can represent the equation something like this, but here the KB has to be a function of and then the operating conditions, and it value may vary from 10 to minus 6 to 10 to minus 10. That's where wider situation, almost 10,000 times difference is coming. So we need to really carefully use this one. However, what are the challenges? We say calculating the contact temperature. When the two surfaces come into contact, they rub against each other, they cause an energy loss. Naturally, local temperature will be on a higher side. So how do we go ahead to really model those things? We don't have any standard approach till today. People have done a modeling, but we don't have exactly the right thing. However, sometimes people say it average temperature, and sometimes they use a flash temperature. That means a temperature which is really getting created at the aspirity. So one is average temperature or total temperature, other cases aspirative temperature. So there is a challenge, how do we envision to be utilized, which temperature should be utilized to calculate overall behavior. Another thing is that whatever we are assuming when using this equation, it may not occur almost every place. So again, here we are estimating the gross behavior. It's not a localized behavior. So if we want a much more perfect behavior, we need to go for localized behavior. One more point comes, so what will be the additives? Quite possible when we use additives, anti-wear additive what we use, then the kb value will be coming down, reduce. As I give an example, something like we can use as a sulfur chloride, we can use a phosphorus, which will really reduce this coefficient. But question comes, are they environmentally friendly? If environmental friendly are not there, then there will be the question that whether we can really utilize this kind of additives or not. And this is the last slide of the lecture. What we say, what will be the challenges to estimate kb? I've seen the literature, people use some experiment, they have done experiment for the maybe say 100 minutes, and then whatever the wear, and they utilize this equation, wear volume, they know after 100 what will be the wear volume, they already know how much load they have applied, what is the sliding distance after 100 hours, and hardness remain constant. They calculate directly kb from this. Somewhat my feeling is not correct really, because this equation can only be utilized for the steady equation or steady state. That's what we have said. Then wear volume will be reduced and then goes stationary, maybe steady situation. Then again, that means this equation only is applicable for this zone, not for a starting zone. The question comes, how do we estimate what will be the running in period? So we really need to know in the beginning itself what will be the wear rate, what will be the wear rate, and whether it has reached to the same level, it is not changing. If it is changing, then it is still going through the and then there's a running in behavior, and that's where we really require to utilize equation. We say this is a wear rate, this is a wear rate is starting, the wear rate of the steady state condition, this takes a time, and b has to be calculated by Cowford method or by substituting data, and after that it is a steady state. So if you utilize this equation, we may get a better value of the kb. And then if we don't utilize this equation and directly calculate kb, that means assuming kb is starting, maybe the steady state behavior is starting from here itself, somewhat that is not going to give correct results. So this is important to account, otherwise there will be some sort of errors, and results will not be comfortable or believable. So with this, I say thank you for attending this lecture. Thank you.